All right. I have the pleasure today of introducing Mike Johnson and Rich Wurzbach. They're going to talk to us today about using advanced oil analysis techniques to thoroughly validate the continued usability of circulating fluids. And I will let Mike and Rich take it away.
Thank you, sir. Welcome to the participants. Appreciate your joining us. This presentation is to explain a methodology for determining the long-term continual usefulness of lubricants. Let me give you a little bit of background here. The context is an American paper mill that is in the process of retooling to produce alternative paper grades. When they shut down the mill, they saved the lubricants from the several large reservoirs and had that in reserve and had the question in mind, is this oil still good for use, or we should just go ahead and dispose of it and bear the cost of replacement? With that in mind, we developed a test slate that would give us the means to diagnose the current health and likely future usefulness of the fluid, to validate that the fluids could not cause harm to the machines if they were set in for a 3 to 5 year run, and then to give the customer some assurance that if they do go ahead and start the mill back up with the fluids from the previously operated machinery, that they were going to be in good shape. So here's a representation of the different classes of fluid. The applications were hydraulic turbine, circulating systems, and thermal control, and component wear protection. Fluid types are identified here generically. The age of the fluid, in all instances, the oil's gotten some long-term use. So they've gotten their value out of it. The question is there more value to be had? You notice in the bottom right, $331,397.50. It's a replacement cost for the fluids if we determine that the fluids cannot be, that are not suitable for future use. So step-by-step process here. First, we reviewed the data history of all of the fluids, all the applications, took a look back in the past to see what was going. And then we constructed a test slate that consisted of the routine test repeated since the oil's been sitting still for more than a year, I guess about 18 months, and secondary and tertiary testing to measure for remaining antioxidants and any potential varnish or sludge potential risk. And then following all the testing, we're to make decisions on replacement requirements. Okay, so the primary test protocol is pretty straightforward. This is what you would expect to use when you are going about the routine condition monitoring activity using oil analysis as your mechanism. Wear metals analysis, the 13 common metals using emission spectroscopy. Fluid physical properties, viscosity, oxidation, additive concentrations via emission spectroscopy, and looking to see if other stuff is there that doesn't belong there. Contaminant analysis via moisture, Carl Fisher testing, particle counting, and then taking a closer look for sodium silicon type replacement. Fairly routine test. From the analysis from this test slate, we saw that the wear levels were low as we expected. Moisture and contaminant levels were low to medium, certainly all rectifiable. Lubricant health indicators suggest that the fluid should be good for continued use with some corrections. So going back to the chart, the display of the products by type, we see the viscosity parameters here where there was some concern that could be rectified. Moisture concentrations all look pretty good and could be improved upon. Particle count concentrations mostly looked good with a few outliers, all of which could be rectified. From our basic test slate, we could reasonably conclude that all of the oil would be suitable for continued use with a little bit of enhancement, a bleed and feed on these to bring the viscosities back in line, and filtering to prepare to go back into service. Basic test slate says things look pretty good. We could continue to use these fluids. So we want to look a little bit further. We want to know if the oil still has some reasonable longevity left in it. Lubricant life cycle obviously is greatly influenced by the antioxidant concentrations, which is influenced by the extent of exposure to moisture and heat during routine use. And so we're going to ask the question, has the oil reached the end of its utility? we're going to be looking at additive chemistry evaluations, specifically the antioxidants. We're looking for the presence of amines, phenols, and alkyl phosphates, such as zinc dialkyl thiophosphate. All of these additive types are placed into the oil as a matter of the manufacturer's preferences for sales cost and longevity of the fluid. They're philosophical choices, if you will. The concentrations of these additives are easily measured, and the concentration certainly impacts how long the oil is going to last. We know that antioxidants are used to turn off low-intensity chemical changes, but once the antioxidants are gone, we expect oxidation to ramp up and the oil to begin looking at the end of its life. The key indicator for corrective action here for us will be what's the percentage of antioxidants left. Now, there's a couple different ways to go looking at antioxidant concentrations. Linear sweep voltammetry, also known as the ruler instrument, and Fourier transform infrared spectroscopy. There are some indirect measures that could be used to measure the effect of remaining antioxidants, but not the concentration of remaining antioxidants. We chose to look for the concentrations. I'm going to let Rich speak for a moment now, talk about the test.
Yeah, sure, Mike. And since this is a conference that is sponsored by the folks from Fluid Tech, and got people like Greg Livingstone in the room, they're going to be very familiar with this kind of graph, which is out of the Fluid Tech ruler, and it's cyclic or linear sweep voltammetry. You see in the lower part the number of seconds as it sweeps through the voltages, and then the corresponding current flow that you see for each of the antioxidants. In this case, it's highlighting both an amine peak and a phenol peak. And by the amplitude here, you're seeing how much is there. And generally what we're doing is baselining the oil to see what is the starting concentration of those antioxidants, then looking at a sample to see how much has diminished over time. This slide then shows us how we're using two markers, these yellow dots, to create an area under the curve so we can calculate the amount of antioxidants, in this case the aromatic amine that is focused in on this part of the ruler graph, if you will. Yeah, and then here we're just, as a comparison, looking at FTIR scan. This is just kind of your generic FTIR scan that shows you what you're looking for. A lot of the time, the common use of FTIR is very effective in engine oils, where you're looking at nitration and sulfation. You've got soot levels building up, and you can see here a comparison of new oil to used oil, even some oxidation and water indications. But when we're talking about the antioxidants, this kind of approach to FTIR doesn't always get that. So you may have to take the FTIR, kind of blow it up, focus in, look in specific areas of the graph. And for example, like the phenols, which you can confirm often, depends on the formulation of the oil, how much interference might be there from other peaks, but somewhere in like the 3650 range, you can focus in on where the phenol peak might be, and kind of get a confirmation of what's there on what you're seeing from the ruler test.
Okay, thanks, Rich. So we conducted the test. Rich's lab, MRG Laboratories, conducted the test looking for three common types of antioxidants. We have the baseline for each of the three, baseline ruler number 1, number 2, and number 3, and then the actual remaining antioxidants in each of these ranges, these antioxidant types. So what we concluded was, obviously, for new fresh oil, we found the baseline, and we found actual concentrations remaining for the ruler number 1 and number 2, and in several instances, substantially diminished antioxidant values remaining behind. We didn't see any of the third category, the alkyl phosphates, such as the ZDDP type of additive would present. So with this result, we could conclude there's some degree of risk in several of these categories for the lubricant not having a chance to withstand another 3 to 5 years of operation. Go back to the first set of tests, we could conclude that everything looked good and the oil would be suitable for continued use. In this set of tests, we're seeing a slightly different story that would cause us to question precisely which ones ought to be put back into service. All right, so far so good. Next question is, if we put these fluids into service, is there any potential harm? We know that eventually varnish and deposits will play out as oil chemistry changes. We begin to produce high molecular weight soluble compounds, and we certainly don't want to be piling up garbage inside any of these reservoirs. So the question is it safe to continue to use this fluid for the foreseeable future? And to answer this question, we're going to the membrane patch calorimetry technology that Greg developed many years ago. It is the MPC test kit, where we have the means to produce a patch. And the patch can then be examined for various different color characteristics using the visual spectrometer. And so I'll shut up and let Rich comment upon this for just a second.
Yeah, so the colorimeter here, or the photospectrometer, which is going to look at the patch that's been prepared and look at the color indication. So essentially, when you have what we would call color bodies that are produced in this kind of oil degradation mechanism, you're initially producing soluble bodies that become insoluble. And that kind of borderline of soluble to insoluble is where things can go from floating around in the oil and being rather benign to plating out onto surfaces. And so this test allows us to create conditions that kind of brings out of solution, if you will, some of those color bodies, some that may initially be in solution. So you don't really see the problem. The oil now doesn't look ridiculously dark or obviously a problem, but these are subtle things that are going to be a problem because you are filling up basically the capacity of that oil to hold on to them, which means they're going to start to deposit. They're going to start to plate out. They're going to need the cool areas of the reservoirs. And there's been a lot of great presentations over the last 3 days about, the varnish, the effects of varnish, how it forms, and so forth. But we're just building on that to use this test and kind of peer into the future a little bit to see, is it worth putting this oil back out there, or are we going to be dealing with issues? What are those issues? They aren't always, catastrophic failure of the equipment. It could just be the deposition of a lot of varnish, which becomes a maintenance challenge and a maintenance problem in the future. So knowing that at this point in time, when we're making this decision about what do we do with these fluids, really helps make that decision, make it an economical decision going forward.
We got some pictures of micro patches that we'll put up here in just a second. But based upon the tests that we did on these various fluids, we see the CIE value noted here, the varnish risk potential noted in the next column, and then just a red, green, yellow, is it high risk, low risk kind of characterization. So with this test, we find 4 of these fluids present moderate to high to very high level of risk for continued use of the system. Here's an example of the worst one of the batch, a 70.5 CIE score. Calculate 140% potential to produce varnish. The other tests for this same fluid also suggested it would be problematic to continue to use it. So this was a confirmation. Couple others here where we didn't see clear risk from continued use, and then the varnish potential score gives us reasons to stop and pause and think about whether we should proceed forward. This is an ISO 320 synthetic circulating oil that had 6 years worth of use, still fairly clear appearance to the fluid, but a 44% varnish score. This is an ISO 32 circulating oil. This is actually the oil that came out of the turbine oil system, and it still looked pretty healthy. Visually, it looked pretty good. We had a 41% potential varnish score here. And then looking at some of those that had a little bit less worrisome look to them. This is an ISO 150 gear oil. Here's a couple. The last two we're looking at actually had really good scores, 6% potential to produce varnish. This was an ISO 220 circulating oil from the main dryer system for the paper machine. And this oil, in contrast to some of the others, was very dark in color, yet it has a low potential to produce varnish within the system. So an example of some of the contrasts of what we're looking for in these various different patches. So if we line all of the test mechanisms up side by side and review the potential for risk that was present based upon those three different views, if you recall, the basic test slate showed some problems, but all of those problems could be rectified with filtration and additive enhancement. The secondary test, the ruler test, showed us where we had real weakness in some of these fluids or the remaining antioxidant additives that would give us reason to think maybe the oil doesn't have long life left. And then the last test, of course, gives us a look into the potential for those fluids to produce relatively short or a high concentration of deposits. Collectively, then, three different views to look at the fluids. The conclusion was that the turbine oil, which looked like it was still in pretty good shape, should not be put back into service for continued use, expecting at least a 3-year run. The AW32 synthetic circulation fluid, EP150 gear oil, and heat transfer fluids also were all condemned, were not to be reused. And so therefore, if you go back to the original value, replacement value of the fluid, $330,000, and we're looking at the retained value based upon putting a little bit of effort into a more detailed analysis, we still were able to save, the customer is able to save a fair amount of money, begging the question, was this exercise really worthwhile? Cost of analysis, $5,200. Retained value, including where we're going to drain off a couple thousand gallons and replenish with new healthy fluid to ramp up additive concentrations, $227,000 retained value, payback term. This is kind of cheating. Payback term is 8.3 days, and internal rate of return, 4,271%. Now, I would be the first to argue we should not be doing this kind of stuff if there's not a reasonable economic value to pursue for our companies. But in this instance, the economic value was superb. I'm going to go back to the previous slide. Think about this turbine oil system here. From all apparent indication that the ISO 32 circulating fluid used in turbine system, 1,900 gallons, this looked like it ought to be perfectly suitable for long-term use. But in the final call, we determined that it wasn't because of the potential risk that it would be throwing off deposits that could have long-term negative consequences. So I guess that's the prime example of where this more advanced set of tests would be useful to help the owner of the assets, the owner of the oil, make very healthy, conservative, economically viable long-term decisions based upon stepping into a more aggressive, more advanced oil analysis test slate.
Yeah, Mike, and if I can comment on that. So, I've about 30 years of experience. My first 10 were in the maintenance department of a power plant. And so from that perspective, I can see where these kind of proactive decisions really can have an even higher level of economic impact. There's no doubt what we've showed here as retained value is there. But what you think about is if this was not done and, they just went through and said, yeah, from the first level of analysis, these oils look fine, so we're not changing them out. And now a number of months goes by. And now we start to see the varnish show up and we start to see the issues. And all of a sudden we get a surprise oil analysis that says, yes, the oil's starting to oxidize. Guess what? The low cost opportunity when the plant was down to make these changes is now gone. And now you have an inopportune time to try to address these issues. So that proactive nature of this, being able to see into the future a little bit, really justifies that deeper level of oil analysis from managing managing these assets, and what that means in terms of the timing and the opportunity to address these issues in the future.
With a final comment, Rich, I would say thanks for punctuating that. And further, I would like to thank you publicly, you and your team, for the rapid and accurate, thorough, superb work you've done there in your laboratory to help us see the future for these reservoirs of oil. And I'm grateful for the chance to work on this kind of stuff with you.
Well, thanks, Mike. And I also want to comment on what you're doing out in front with these customers when they come to you and say, help us develop a strategy, because it often takes the kind of messenger that you are when you're engaged with the customer, looking at their challenges, getting down into what they're trying to achieve with their assets, to help explain and help that customer understand why the oil analysis is of value, why the more detailed analysis, rather than that just being an exercise into finding the lab that can do the thing the cheapest. So I think it really is the teamwork that gets this communicated to the customer and ultimately to their benefit. So thank you.
Yes, sir. Are there any questions? Okay.
You're letting you off easy.
Well, that's good. Let's see.
I like Greg Livingstone's comment to say we should have charged more for analysis, but you know what? I'm happy with providing, value at the level that we're charging. I would just like to see more asset owners recognize that the value is there and engage this more often, rather than just defaulting into, the very basic oil analysis and not getting the full benefit. But yeah, let's just do this more. Let's find more opportunities to educate folks so we get more participating in this kind of work.
Thank you, Mike and Rich. You guys did a great job.
Yes, sir. Everybody have a great day.
You too.
All righty.
Bye-bye.